Now we want to talk about the dot product of two vectors. So we're going to use our F12 and F13 vectors from before. The dot product is not going to have any direct interpretation in terms of these vectors, at least no physical interpretation, but it will lead us to something that has a very significant physical interpretation. So let's just say we've got two vectors. Now we're not talking about F12 and F13 at this point. We're talking about any vector A and any vector B in the plane. Okay, and of course this can be extended to space, but we're just going to talk about the plane right now. Okay, A is going to have an X component and a Y component. So we're going to call those little ax and little ay. And the X component, of course, the vector X component is ax times the I vector. The Y component is ay times the J vector. Similarly, the B vector is bx times the I vector plus by times the J vector. Okay, now we're just going to define the dot product rather than motivating it, and this is just an arbitrary choice. We could motivate it and define it based on a trigonometric, very simple trigonometric definition, but we're going to go this way. Okay, so the dot product is going to have the following. Basically, this is the definition for dot product in the plane. It simply says that I dot I is 1, J dot J is 1, and I dot J equals J dot I equals 0. So if you're dotting the same between the unit vectors I and J, if you're dotting the same vector with itself, the result is 1. If you're dotting two different, either I dot J or J dot I, you're going to get 0. Okay, so it then follows that A dot B, now we're going to say also that you have commutativity and associativity and distributive laws and so forth, but just proceeding in the manner that's intuitively obvious here. A dot B is going to be AXI plus AYJ dotted with BXI plus BYJ. And what's that? That's AXI. Well, I'm going to go ahead and shortcut this a little. I haven't specified all the laws that we're using, but again, this is completely analogous to what you do with numbers. I started doing AXI dot BXI, and then I decided I didn't want to write all that out, especially because of space limitations, and I just wrote the wrong letter. Okay, it's AXI dot BXI, but that's just AX times BX, and then that's I dot I. And then we're going to have AXI dot BYJ. Well, that's just AX BY times I dot J. And then to this we're going to add AYJ dotted with BXI. That's going to give us AYBX times J dot I plus then AYJ dot BYJ, which is AYBY times J dot J. And that, since I dot J and J dot I are 0, then this term is 0, and this term is 0. Since I dot I and J dot J are both 1, the result of that is just AX BX plus AY BY. Now, a lot of times you'll just see this as the definition. I prefer to use a little deeper approach and just define this in terms of the simple facts that I dot I and J dot J are 1. But if you combine an I with a J and a dot product, you're going to get 0. That's a simple thing to remember. And it's kind of essential, and it's going to be very profitable to think of it in these terms. When we talk about cross product, you'll get a better understanding there too. So that A dot B is ultimately this. And of course, we're going to usually use this, but we always want to remember where this comes from. It comes from these definitions and just the usual associative and commutative laws. Okay. Okay, well, there's another thing. It turns out that A dot B equals the magnitude of A multiplied by the magnitude of B multiplied by the cosine of theta, where theta is the angle between these vectors. Okay, so if we know the components of the two vectors, we can easily calculate A dot B and the magnitude of A and the magnitude of B, which means that just by dividing both sides by these product of these two magnitudes, we get the cosine of theta, and then we can easily determine theta, the angle between two vectors. And I mentioned that this can be done in 3 dimensions. It extends to 3 dimensions very, very easily. Matter of fact, it can extend to any number of dimensions, and the definition and the whole feel of the thing doesn't change. So we can get the angle between two vectors in 3-dimensional space, or go to 4, 5, 6, 58-dimensional space, whatever.